This video lesson is titled Begin with the End in Mind, which is a good habit of people that plan ahead, but the title comes from the fact that we're talking about end behavior of rational functions with this lesson. It's the second half of lesson 4.4. Mastery objective is to find horizontal asymptotes and sketch complete graphs of rational functions. One issue with the graphing calculator for rational functions is what you see here. The graphs are not really well drawn on the graphing calculator, so it's real important, as was mentioned earlier, for you to use algebra to come up with the properties and the characteristics of the rational function that you're asked to graph. Because frankly, if you if you put in one particular rational function, which this is a graph of, you can see that the calculator with a standard window will not really display something that's easy to see. Actually, this is what the graph is drawn as a complete graph of what you see. So these that represent the same two, and you can see that here are two vertical asymptotes, and the way they're shown on the graph, on the graphing calculator, is not real consistent, number one, and you see kind of a vertical line where you're not really sure if that would be part of the graph or part of the or the asymptote. And then here, when you see the graph kind of doing this, you kind of lose sight of it, which you can see right here. So it's real important that we develop these. So end behavior. Let's talk about end behavior. And this is taken from polynomial functions. You might remember that when the absolute value of x is large, the graph of a polynomial function will closely resemble the graph of its highest degree term. So if a polynomial is of degree 5, remember, then we know it's going to look kind of start low and end high. If it's of degree, an even degree like degree 6, it'll start high and eventually end high, and we can make predictions of the end behavior that way. When it comes to rational functions, kind of similar language but slightly different. When the absolute value of x is large, the graph of a rational function closely resembles the graph of the ratio. Remember, rational functions involve ratios. The ratio of the highest degree terms in both the numerator and the denominator. And that takes some more exploration. We'll look at that now. So it's all about the degree of the highest term in the numerator and the denominator. And really, there are three things that can happen. There are only three things that can really happen. Number one, the degree of the numerator could be greater than the degree of the denominator. The degree of the denominator could be greater than the degree of the numerator. And again, we're talking about the degree of the polynomial that represents the numerator and denominator. And of course, the third is that the degrees of both of those could be equal. So let's look first of all when the degree of the numerator is greater than the degree of the denominator. Here's an example of a function whose numerator is 4x squared minus 7x plus 9, and the denominator is 5x plus 8. Well, all we're going to concern ourselves with is looking at the highest degree term in each the numerator and denominator. So that would be 4x squared and 5x. And we're concerning ourselves with only these terms because, frankly, when we let x be very, very large, the fact that we're subtracting 7 minus a very large number plus 9, or adding 8 to these very large numbers, will kind of not make a big difference. So really what's running the show, as it does with polynomials, are these two terms. So we look at the ratio of 4x squared and 5x, and we can further simplify that into, if we divide an x from each term, 4x over 5. Now, if we let x be very, very large, you can see that the numerator is going to become larger and larger, where the denominator is going to stay at 5. So really, 4x over 5 will, as x becomes larger and larger, or smaller and smaller, will increase or decrease without bound. That means become larger and larger and larger with really no end in sight. Just imagine if you let x be very large numbers, this number will be very large. If x is very small, like negative 1,000, then this would be a very small number. So the function will increase or decrease without bound. If the degree of the denominator is greater than the degree of the numerator, Well, here's an example of that. Notice the degree of the denominator is 5, degree of the numerator is 2. So again, we're talking end behavior. Oops, that 7 slid over a little bit. Let's slide it back. Okay. If we consider just the ratio of the highest degree term in both the numerator and denominator, we'd have this. Let's fix that. There we go. Oops. And that would equal, if we divided x squared from the top and the bottom, we'd have 3 divided by 7x cubed. And now we go back to our big little principle. If we let x be large numbers, then we'd have 3 times 1 over large numbers, or big. 1 over big, remember, is small. So when we let x be very, very big numbers, this would approach smaller and smaller numbers. And really, it doesn't matter what these are doing, because as we get out there very far, it doesn't matter that we're adding, we're subtracting 6 times a big number and adding 11, because we're also dividing by adding 2 times that big number cubed. So we just have to look at the behavior of the ratio of the first 2 terms. And we get that as x becomes larger and larger, or for that matter smaller and smaller, we've still got the 1 or 3 times 1 over big principle, which is small. So the function will approach y equals 0, 1 over big is small, or the x-axis. So we have a horizontal asymptote, which is the x-axis. Get back to where we were. Here we go. And the last scenario is when the degrees of the numerator and the denominator are equal. So let's look at one of those. 6x squared minus 7x plus 5 divided by 3x squared plus 8. Notice it's a rational function. We've got a polynomial divided by a polynomial. And we're concerned about end behavior again, just trying to keep us on track. So if we take and look at the ratio of 6x squared and 3x squared, we get this, which is equal to 2. And because of that, our function is approaching the ratio of the leading coefficients. Notice the leading coefficients, when they're the same degree, are the ratio of 6 to 3, or 2. So we would have a horizontal asymptote at y equals 2. So this summarizes it. You can pause this and jot these very important 3 bullets down. If we have a polynomial function, a rational function, 2 polynomials, whose numerator has degree n and whose denominator has degree k, because those are the degrees of the leading terms, then here are 3 scenarios. So you can pause this and take notes on what those say, because those will help us decide whether we have a horizontal asymptote at y equals 0, or the x-axis, a horizontal asymptote somewhere else, or the graph increases or decreases without bound. Okay, now that you've jotted those down, let's look at 3 different examples. Here we have one where the degrees are the same. And remember, when the degrees of the numerator and denominator are the same, we just need to look at the ratio of the coefficients of the terms, and that would be 4/3. So we'd expect to have our function have a horizontal asymptote at y equals 4/3. Here's the graph. From previous in this lesson, you can see that what makes this denominator 0 would be when 2 minus 3x is equal to 0, or when x is equal to 2/3. So here's 2/3, x equals 2/3, and here is our y equals 4/3. We'll worry about the rest of the graph as we go on. Here's one where the denominator's degree is greater. Remember, when the denominator's degree is greater, we expect that our horizontal asymptote is going to be the x-axis. And here you have a case where, got a lot more going on here. Again, our 2 asymptotes are at 3 and -3. Here's -3, here's 3, x equals 3, x equals -3. Our 0 is what makes the numerator 0, is x equals 0. It's crossing right there. So notice with horizontal asymptotes, the graph can actually cross the asymptote. It's just that the graph approaches the x-axis as you look at the end behaviors, as you go way left and way right. Last situation is when we have a numerator has a degree greater than the denominator, and we expect that to grow, increase, or decrease without bound. Asymptote would be at x equals -4 for vertical asymptote. We have some zeros, it looks like, in the numerator. It looks like that would factor into x minus 3, x plus 2. So 3 and -2 would be x-intercepts. Let's take a look. This would be, I guess, our -2. This is our 3. And you can see that the graph increases to the right and decreases without bound to the left. This dashed oblique asymptote, slanted asymptote, we'll talk about in class. So when it comes time to now graphing polynomial functions, here are our 3 basic steps. We're going to use algebra to determine the vertical asymptotes, any holes, and the x-intercepts and y-intercepts. We'll determine the end behavior. Again, 3 scenarios. Either the graph will increase without bound or decrease without bound, or it will approach the horizontal line, the x-axis, or some other horizontal line. And we'll use our calculator then to help us complete the sketch. So here's an example. We'll look at this example here, and I will promise you we'll look at a slightly more complicated and involved example in the beginning of class next time. But when you look at this numerator, first of all, what makes our numerator 0 would be our x-intercept, and that would be -2. So we'd have -2 for an x-intercept. We look at our denominator and we sense that there might be 2 zeros, and there are. This factors into x plus 4, x minus 3. Right? So we would consider our 2 vertical asymptotes as x equals 3 and x equals -4. Remember, to have a hole in our graph would only result if one of these factors, which would make one of our x values 0 in the denominator, existed in the numerator, and we don't have any of the same factors so we have no hole in our graph. So again, to recap, we have an x-intercept at -2. We've got 2 vertical asymptotes, one at x equals 3, one at x equals -4. If we look back at this, remember when we let x be 0, f of 0 would give us our y-intercept, which would be 2 divided by -12, or -1/6. So we found our vertical asymptotes, we've got our y-intercept, we found our x-intercept, and now for end behavior, the degree of the denominator is 2, the degree of the numerator is 1. So we would expect then to have the x-axis be a horizontal asymptote. So as we get larger and larger, this graph would be getting closer and closer to the x-axis. As we get smaller and smaller, same deal. So this summarizes what we find. This is kind of like using algebra to come up with all the things we should find. And then we kind of use our graphing calculator, and yes, if that looks familiar, that's the very graph that we began this video lesson with. That I said, hey, listen, it's kind of hard to really appreciate much that we get out of this graph at all. Very difficult to read, but again, now you know. See, now we take this information that we find algebraically and use it in conjunction with this visual aid, we can get a more complete picture, which is this. Again, drawing your vertical, I would draw your vertical asymptotes in first at x equals -4 and x equals 3. We determined that -2 was a 0. So we're looking right here at -2 on the graph, saying, well, we know, if that's -2, right here is -2. We know that the graph is going to cross there. We also have a y-intercept of -1/6, which means slightly below the x-axis. At -1/6 is where the graph crosses. We could use our table of values to kind of get a few values here, but now we can see that as we approach the vertical asymptote x equals 3 from the left, it's increasing without bound. As we go to the right, it's approaching that asymptote, same here. So with a few values, we could put those together. Just the beginning, that's just the beginning of being able to graph some rational functions. We'll look at another example in class, and we'll see you then.